Welcome to this power learning session on Algebra 2B Concepts, Lesson 3, specifically change of base. Today we're going to focus on using the power property of logarithms to simplify expressions. First of all, let's remember what is a logarithm. A logarithm is an exponent. 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 Hopefully, I've annoyed you enough that the next time you hear the phrase a logarithm is, you'll think an exponent, because that's really all it is. Okay? It's just describing an exponent to which a specific base is raised to obtain a given value. What do I mean by that? So, a logarithm is an exponent. In this case, this logarithm ends up being 6. So 6 is an exponent to which a specific base, in this case 2, is raised to obtain a given value x. So 6 is the exponent that will raise 2 to get x. Okay? So 2 becomes our base, 6 is our exponent, and x is just our value. Sometimes I call x, this number, the result. It doesn't have a proper name. So again, 2 is our base, 6 is our exponent, and we'll call x, this number, the result. Notice the way that we can flip-flop back and forth between logarithmic and exponential form. As long as we have the base, the exponent, and the result, the base, the exponent, and the result, we can go back and forth between these two forms. Now, there are many properties pertaining to logarithms. In fact, if you remember your laws of exponents in this column, the laws of logarithms are actually pretty similar. For example, you see that when combining two exponents by multiplication, we end up adding those exponents. When combining two logarithms by multiplication, you see it's equivalent to adding those two logarithms separately. Same thing here. When dividing exponents, you see that you end up subtracting the value of each exponent. Here, by subtracting two logarithms, it's the same thing as dividing the logarithm of the same base and taking the quotient of the results. Okay? Notice in this case that each log all has the same base. In order to apply these laws or these properties, our logarithms must have the same base. Now, you see that many of these logarithms are just written like this, where no base is specified. If nothing is written here, you assume that the base is 10. This is just the base that we count in anyway, so if we don't write it, again, we're assuming we're just using our normal base. There are many other bases, as you've seen, log 2, log e. These are also very common. Again, if it's unwritten, assume it's log base 10. Now, aside from these multiplication, division, exponent, etc. properties, we have a change of base formula, we have inverse formulas, but the one we want to talk about today is the power property. So the logarithm of a power is the product of the exponent and the logarithm of the base. The logarithm of a power is the product, so multiplication of the exponent, and the logarithm of the base. So if you take a look, for example, if we had log 10 to the third power, that's the same thing as log of 10 times 10 times 10. Thanks to the addition property, we know that's the same thing as log of 10 plus log of 10 plus log of 10, which just means we have 3 log 10s. Okay? Algebraically, that just means if we have this exponent, we can transplant it and just put it as a multiplier in front of that logarithm term. Okay? So why is this okay? Before I do this example, let's take a look. So as we know, we can convert, let's say if we had a to the b equals c, we could convert that to log base a of c equals b. But what about exponents? Okay, let's raise our expression to an exponent. Let's say I introduce d. Let's say I raise this to d, and I raise c to the d. So now I have a to the b to the d equals c to the d. a to the b to the d equals c to the d? Well, thanks to exponent rules, I know that a to the b to the d is the same thing as a to the b times d. Again, this is a rule for my exponents. So a to the bd equals c to the d. Okay, great. But what about converting this to a logarithm? What would this look like? Well, if I wanted to know what log base a of c to the d is, remember what's a logarithm? It's an exponent. The question here is what exponent, if I raise a, what exponent do I need to raise a to get the result c to the d? So I want this to be the answer. I have a as my base, and they're saying, okay, what's the exponent you need for a? Well, you need b to the d. Okay? So take a moment and look that over. So that's the same thing as d times log a of c equals b d. Now, on to our example. Now, and if that little piece I just worked out for you didn't really click, if you're still a little confused on it, just remember that we are allowed to, if we have a result being raised to an exponent, we can bring that exponent down and put it as a multiplier in front of the logarithm. And that's what we're going to practice now. So say we have to take, to evaluate log base 2 of 32 to the 6th power. My first step is going to be to take that exponent and bring it out in front of the logarithm. So now I have 6 times log base 2 of 32. This looks a little bit more familiar, right? So from here, I'm just going to separate off my logarithm and simplify that. And I'll bring down the 6 in a moment. So let's just focus on log base 2 of 32. Log base 2 of 32. So I have a base of 2. I'm being asked to find an exponent where if I raise 2 to that exponent, I get 32. So 2 to what power equals 32? Well, that's 5. 2 to the 5th power equals 32. So log base 2 of 32 is equal to 5. Now I bring down my 6, can't forget about that. So now I just have 6 times 5. Well, 6 times 5 is 30. And now I've done all my work. So log base 2 of 32 to the 6th power is simply equal to 30. Let's practice again. What about log base 3 of 9 to the 4th power? Again, let's start by bringing that exponent out in front of the logarithm. So I have 4 times log base 3 of 9. I'm going to ignore 4 for a moment, just for a moment, and I'm going to evaluate log base 3 of 9. Log base 3 of 9. So I'm being asked, if I have a base 3, what exponent do I need to get the result 9? Well, that's a pretty easy one, right? We know 3 squared is 9, so the exponent I'm looking for here is 2. Bring down my 4. 4 times 2 is 8. So log base 3 of 9 to the 4th power is equal to 8. Let's do another. What about log base 4 of 64 to the x? Notice I've thrown an x into this expression, and that's just to demonstrate to you that even if there's a variable, in this case I have the variable as the exponent, but it wouldn't have mattered if it was the base or the result. I'm going to deal with it the same way. So just as before, I have an exponent, I'm going to pull it out in front of the logarithm. So x times log base 4 of 64. Just as before, I'm going to ignore that x for a moment. I'm going to ignore the multiplier. And I'm going to evaluate log base 4 of 64. So the question is, 4 raised to what exponent, remember because a logarithm is equal to an exponent, equals 64. 4 to what exponent is 64? Well, 4 to the 3rd, right? 4 squared is 16, so 16 times 4 is 64. So 4 to the 3rd power. I bring down the x. I have x times 3, so my answer is simply 3x. So log base 4 to of 64 to the x equals 3x. Again, had this variable been located elsewhere, you still could have done this problem. You would have done it the same way, just treating x as you would any other number. Don't let the variables frighten you off. All right, let's do one last example of this. Once again, we're given a logarithm expression that has an exponent in it. Step 1 is going to be to bring that exponent out in front of the logarithm. So I have 6 times log base 5 of 25. So I need to evaluate this. What am I going to do? I'm going to ignore that 6 for a moment, and I'm going to evaluate log base 5 of 25. So my question is, my answer needs to be an exponent. So the question is 5 to what exponent equals 25? Well, that's pretty simple. It's 2. So notice I've answered the question. My exponent is 2, so 5 squared is 25. Make sure on this step that your answer is the exponent, because a logarithm is an exponent. So I have 2. I bring down the 6. 6 times 2 is 12. So log base 5 of 25 to the 6th power is equal to 12. So that's it for this power property. Let me know if you have any questions.